Hi everyone. In this lesson we're going to be working with applications of exponential functions to real life situations. We will be working with exponential growth and exponential decay. Growth, well, it means that something is growing or increasing. Getting bigger. Decay is the opposite, and that means that it's decreasing. It's the opposite of growing. That means it's decreasing. We're now going to be working with this exponential formula where A represents the new amount that we will be finding in every problem. P is the principal amount or the starting amount. T is the exponent that usually is going to represent time, usually in years, but not always has to be in years, but in this case it's going to be in years. R is going to be the rate, and that's going to be a decimal. That's the rate of growth or decay. And here I have a 1, which is part of the formula, plus and a minus here. We will use plus if it is growth and a minus if it is decay. So every time that we use this formula, we only use one sign, either a plus or a minus, depending on the situation. So it is a plus if you have growth and a minus if you are dealing with decay. This is the same equation that I mentioned before. Usually the exponential function would be this: y is equal to a times b to dx. That's when we're graphing on the coordinate plane. And in this case, the a is going to be what usually is the y, and the p is what is usually the a. The b is going to be all this here. It's everything that is inside the parentheses, that adding or subtracting to the 1, the value of r, is what would be b, and the exponent here is the x. In this case, it's the t. This is for graphing on the coordinate plane, and this is for solving the equations, solving word problems, but it is exactly the same. Each part just has a different name, but it's the same format. The r is very important. Is the rate at which something is growing or something is decaying. And that's usually going to be, as we see here in problem number 1, it's giving us a percentage, but you have to put it as a decimal. Here in the formula, we have to put it as a decimal. So we need to change percents to decimals. If you have, let's say, 4%, 4% means 4 out of 100. That's what the word percent means. And if you put this in the calculator, you get what the decimal equivalent is, which is 0.04. That is just by putting into the calculator and dividing. A percentage is always divided by 100. So if you have 22%, that's 22 over 100, which is 0.22. Those are the things that we need in order to be able to use this formula. And whatever this decimal has to be added to the 1 or subtracted from the 1, depending on the situation. I have 4 problems here. I have 2 of them, which are going to be the examples, and I will leave the other 2 for you. Number 3 and 4 will be your exercises for your practice, and I will do 1 and 2. The instructions: write an exponential function to model each situation. Find each amount after the specified time. Exercise number 1. Suppose you have $1,500 in a savings account paying 4% annual interest. Find the account balance after 15 years with the interest compounded annually. There's some things also that are unique for exponential situations, which is, for example, here this word compounded annually. In this case, we're talking about having money in an account bank, and that's very important because that will give us whether we use a plus or a minus on the formula. This part, do we have to use a plus or the minus? Well, when we have money on the savings account and it's paying interest to us, then that money is getting bigger. It's increasing over time. So we had to use, in this case, a plus because it's a growth situation. The money that we originally put in the bank account is going to grow. So it is going to be a growth situation. Therefore, we will use the plus inside the parentheses. The rate is going to be 4%. We know that that is 0.04 because we did that up here. And we want to find the amount in the account, that's the balance, how much money you have after 15 years with the interest compounded annually. What does it mean? It means that, for example, if they are paying for 4%, the first year they're going to pay 4% of the 1,500, which is $60. So after the first year, you start with 1,500, and after the first year, you should have this quantity plus the 60, because $60 is what 4% of this quantity is. So we're going to add that 60, and this is what you should have now after the first year, which is 1,560. And then for the second year, it's going to be 4%, not of the original quantity, 1,500, but from this quantity. That is what compounded annually is. It means that it's paying interest not on the original, but on what you have at the end of the first year. And whatever you get here at the end of the second year, the 4% for the third year is going to be paid on this amount over here, not on these other two. So that will mean that the amount in the bank account will grow faster because it's not paying interest only on the original quantity, but also on the interest. So it's paying interest on the interest, which was the $60. That is what compounded annually means. So we could do this as I was doing here. First year, we could do second year, third year, and so on. But it will take us a long time to find for 15 years. And that's why we use this formula, because we just substitute the parts that we have, and we should be able to find the answer very quickly instead of doing 15 times finding the interest, because we need for 15 years. So let's write the formula. The formula is A is equal to P1. In this case, we know it's growth, so we're going to use a plus, R raised to the T power. A is the amount that we're going to be finding, the new amount after the 15 years. P is the principal amount. The principal is this. That's the starting amount. So it is 1,500. The 1 is part of the formula. And then the R, which is the rate, written as a decimal, is 0.04. All this is going to be raised to the 15 because it's the time. In this case, it's 15 years. How much money will I have after 15 years if the interest is compounded annually at a rate of 4%? So in this case, we will follow the order of operations to simplify this. That's the only thing that we need to do. So inside the parentheses, we add these two, 1 plus 0.04. So just doing that, we have 1,500 multiplied by 1.04. That is adding this raised to the 15 power. Now I'm going to take this and raise to the 15 power. 1.04 raised to the 15 power. I'm just rewriting 1,500, and this raised to the 15 power is 1.80094. I'm going to keep here at least 4 or 5 decimals after 5 digits after the decimal point. We cannot round here. The final answer should be rounded here only one time. And now I multiply this by 1,500, which gives me new amount equal to 2,701.415258 and so on. But we're talking about money. This is the amount of money after 15 years, and money does not have many decimals here. Money only has only 2 digits after the decimal point, because we can say we have $10.99, but we cannot have more over here. And if we add 1 cent more, then that becomes $11.00. So the maximum that you could have when we're talking about money is 2 digits after the decimal point. So we're going to cut this number here, but we cannot just cut it like that. We need to pay attention to the following number. If this number is 5 or bigger, we add 1 more to this. If this number is less than 5, we keep the same number. 5 or bigger, add 1 here. This one is a 5, therefore I need to add a 1 here. So this is going to become $2,701.42. That is what you will have after 15 years. So find the balance find the account balance after 15 years with interest compounded annually. The answer would be the balance will be $2,701.42. And that is number one, a growth situation. Let's look at number two. Number two says a $25,000 car decreases 12% in value per year. Determine the value of the car after 6 years. Something that you buy, like a car, like a computer, a printer, any artifact that you buy, loses the value. It doesn't increase the value over time, but it loses value, so that if you have a new car and then you have the same car after 10 years, it's not going to be worth the same value. It's going to be worth much less than what the original value was. So this is a decay situation. We're losing value over here. So this is for decay. Therefore, we have to use a minus in the formula. It's decaying at a rate of 12% per year. So we can take this and put it as a decimal. 12% means 12 divided by 100, which is 0.12. And this is going to be also compounded annually. Instead of growing, it's just decreasing. But for example, if you have that the original value of the car is $25,000, and then it decreases 12%. After the first year, is going to be worth only $22,000, because 12% is $3,000. It's going to lose $3,000 of value, so that after the first year, the car is only worth $22,000. And then for the second year, is going to lose 12% of this one, not of the original value, but now 12% of the 22,000. And that's what you will get here. And it's going to keep like that, being compounded annually, meaning that it is reducing 12% of the amount that we have after this a certain number of years, not of the original quantity, which means it's going to lose value faster. So we could keep doing this, finding this and finding that 6 times, because it's 6 years, but we could do it faster with the formula, and so we're going to do with the formula. So the new amount is going to be the original amount multiplied by 1 minus the rate raised to the time. So we need to find the new amount. The original amount, the original value of the car is $25,000. It's losing value at 12%, which is 0.12. And we need to find what is the value of the car after 6 years. So the exponent is going to be 6. And now we also follow the order of operations. Here we have to subtract. Instead of adding, we subtract. So we're going to get something that is less than 1 here, whereas if you If you add, you get something that is greater than 1 here. So 1 minus 0.12, that gives me 0.88. So $25,000 times 0.88 raised to the 6th power. I'm going to raise 0.88 to the 6th power. So it's $25,000. This is 0.46440, keeping 5 digits after the decimal point. Now multiply this by 25,000. And doing that, I get $11,610.10217. But again, this is the value of the car. We're talking about money. So we again need to cut this here to the nearest 100. We look at the following number. This is only 2. It's less than 5. So we need to keep exactly as it is, 0. Therefore, the value of the car after 6 years is $11,610.10. I'm going to erase this so I can write the answer. Determine the value of the car after 6 years. The value of the car will be $11,610.10. And that is how we use exponential functions to solve problems involving real life situations. I'm leaving for you exercises 3 and 4 down here. Please practice with them.